in homogeneous 3D and 2D Bose gases?
All right, thank you very much. Good afternoon, everyone. Thanks to the organizers for inviting me, and like Talia, I have to apologize for actually missing all of it. So I might actually say things that were said before, including jokes. You know. I would also like to especially thank Natalia for running 10 minutes over time and setting the tone. so there's no pressure on me now. All right. So I'm going to talk about wave turbulence in homogeneous 3D and 2D Bose gases. And it's actually a little bit of introductory overview, but maybe I will assume too much about what you know, because I do want to show some new things. I think some of you are familiar with the systems. Some of you have seen our labs yesterday. Unfortunately, I also couldn't be there for that. So this is one of the things that, well, we have just seen this drawing. I might not be even the second one, but like the 10th one to point out in this workshop that it's actually exactly 100 years since Louis Richardson described this direct turbulent cascade in verse here in Cambridge. So I guess you all know this poem. Big worlds have little worlds which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. Now, in my talk and in our work in general, basically the same idea applies for direct cascade from large to small length scales, except we don't work with worlds, at least not deliberately. For the most part, we think. We are working with wave turbulence, and we interpret as best we can our results in that context, even though in the future it'd be interesting to look at both, and maybe already there are some effects of vortices in our system that we don't understand. So these are our tools. This is going to be fast. Again, this is what some of you, if you've seen the machines, some of you have seen machines yesterday. We're using 3D and 2D gases. Atomic gases, we trap them in so-called optical boxes, which means that the gases, before being driven to turbulence, are homogeneous, which is in contrast to a majority of the field of cold atoms when they're harmonically trapped. And that's advantageous for various things, and in particular, it's advantageous for turbulence because it's a phenomenon that you naturally think about in momentum space. Okay, so we use these systems where momentum, to a better approximation, even though they're still finite, is a good quantum number. Okay, I'm not going to go into details of that. If somebody is really interested, recently we wrote a review about it. So this is a 3D box. This green is repulsive light. So basically, atoms are confined to some regions of empty space by a tube and two sheets, which we invented here in Cambridge now a decade ago. And we'll also use a 2D box, which was a bit later actually pioneered at LKB in Paris, and we just copied their thing. And another important thing is that is the atom for most of the experiments. So there will be a couple of, maybe one slide on all the experiments, but for the new experiments, all the experiments are done with potassium-39. And potassium-39, because of some numerology of atomic physics, has a convenient feature that it's easy to tune the strength of interactions in the system, the strength of nonlinearity in these gases using so-called Feshbach resonance. It's just a matter of applying some external magnetic field. Okay, those are the inanimate tools, and these are the people who actually do the work. It's quite a few that have contributed since we started the studies of turbulence about 6 or 7 years ago. Many of them are gone. In particular, we started this with Nir, who now has his own group at Yale, and the two experiments that I will mostly talk about are sort of the final PhD projects of Lena Dogra and Maciek Galka. Maciek is here and can answer hard questions. Okay, so you already answered all the hard questions. Okay. Yes. Okay, so starting at the beginning, going back to 2016, this is the basic idea of the experiment. So we have this cloud in a box, and then we shake it, like water in a bathtub. Okay, so we just have some linear potential or constant spatial constant force, but oscillating in time, which on a very large length scale somehow introduces energy into the system. And what I'm showing here is a Gross-Pitaevsky simulation, which actually is from those days. Okay, which is, I'm not saying it explains everything. Actually, you will see that it doesn't. But it sort of gives the idea of what we're doing, and some typical time scales. Yeah, so this is slowed down 32 times. And qualitatively, what you see is two things which are characteristic of turbulence. I don't know how to restart the movie differently. One is that we see a direct cascade, so the initial excitations are a very long wavelength, and then gradually there are finer and finer excitations in the system. And the second thing is that we're shaking just left and right, but eventually, at least at small length scales, the excitations are just as equally populated going up and down. This idea of isotropy, again, we have seen probably many times, but also in the talk that just preceded me. Now, this is in situ. Okay, this is what simulation says is roughly happening in the box. Experimentally, the simplest and still most commonly used method is the so-called time of flight, which was also mentioned before, which just means you turn off the box and you see how the gas expands, and that tells you something about the momentum distribution. So what you see over here, this diamond, is how a pure Bose-Einstein condensate expands from a cylindrical box, okay, this is driven by interactions. And then when you mess it up, okay, and again, giving you some sense of scale, what means a strong drive is something where the potential drop is comparable to the chemical potential. That's the scale, okay? Much less than mu is weak drive, and if you go to mu or more, that's a strong drive. And this is slowed 32 times, so the typical shaking frequencies are maybe tens of hertz. And so if you do that for a couple of seconds with a relatively strong drive, you mess it up completely. And so we say, like, well, this is some kind of turbulent state. Now, if you know something about cold atoms, you could be skeptical at this stage, because you could say, like, well, you just heated the thing up, right? So this could be just a normal thermal state that is not particularly exciting. However, the first hint that is not the case is this, while it is completely messed up, there doesn't seem to be like any phase coherence left in the system. It's still a very, very low energy state, and that is first hinted by this dotted circle, which actually corresponds to energy, to kinetic energy of half the critical temperature for Bose-Einstein condensation. So most of the atoms are actually well below that energy, even though the state looks messed up. And the actual energy per particle is something like 10% of the critical temperature for condensation, which means that if you take the total particle number and the total energy, you would say, like, if this cloud was in equilibrium, it would actually still have 70% condensed fraction. You started with 100, it cannot be still 100 because you pumped in some energy, but it would still be 70. And indeed, if you let this thing relax, I'm not going to talk much more about relaxation today. It is something that we're also interested in. But if you do relax, the system you get by stopping the drive, indeed you get back exactly the condensed fraction that you can predict yourself with a simple calculation. Okay, this is the first hint that this is not a simple thermal state, but quantitatively, as you know, the smoking gun for turbulence is that the momentum distribution is some kind of power law, which is definitely not a thermal distribution. And so again, this is the original data from 2016 in 3D rubidium-87, and what we said there, based on whatever data we had, is that this power law is something like 3.5. Now we have about 2 orders of magnitude more data. So as opposed to this one measurement, we have about 150, also with different interaction strengths and so forth. And we would revise this number to something like 3.2 plus minus 0.2. This is still unpublished result. And then this number actually agrees pretty well with the prediction for the Kolmogorov-Zakharov weak wave turbulence, where asymptotically, if we could go to, it's not even, it's like, I don't know which way is this, north? It's probably around Manchester or so, that you would get like gamma equals D, then we get gamma equals 3, right? Asymptotically it's true, but any finite system where you have finite K range, you get some corrections to gamma of 3 due to some logarithmic functions that are part of the solution. And so we have looked at this in some detail, and this kind of number makes sense for our momentum range. Now, more recently, you have maybe heard about it already yesterday from Maciek and others. We have done a similar thing in 2D. Yeah, again, it looks like a power law. Again, it's larger than 2. It's even more larger than 2 than it is in 3D. And again, this at least qualitatively makes sense because various logarithmic corrections are more pronounced than in 2 dimensions. Okay, so just seeing this power laws is the sort of thing that you see in all kinds of systems, physical and non-physical, like financial markets or whatever. Okay. And so the question is like, with this system, what's new that we can do and maybe contribute to the field at large. And so these are the 3 topics I'm gonna touch on today. Okay, this is the steady state distribution again. The first point is that often even though we have just seen a counterexample, with light, where one can nicely see the time evolution. But often in many systems, you see, a fully developed turbulent state. But less often, one is able to actually see how that state emerges starting from an equilibrium system. And so in our case, we can, look at things at all relevant length scale and time scale. And so we can look what, we loosely call the birth of turbulence. This is Maciek's recently published paper. The second point is that if you just see the steady state, which is not thermal, but it's stationary, then you know that the reason this is possible is because there's some underlying momentum, scale invariant momentum space energy flux, which is sustaining this non-thermal state. Okay. And you know that this guy is constant in time and also in k-space, but you don't necessarily know what it is. Okay. Any non-zero value is in principle consistent with your observation of just the momentum distribution. And so again, I don't want to qualify exactly how rarely, but not that often in various other systems one can actually measure these underlying fluxes, which we can. Okay. This is the second new thing. And then the third thing, which is still unpublished work from led by Lena, is that using all the tools we have, we're going to try to construct some kind of equation of state for this far from equilibrium system. So some kind of equilibrium-like description, succinct equilibrium-like description of this far from equilibrium system. Now, for some of you, when you see what I mean by that, you might not call it an equation of state. You might just call it equation, because it might be your daily bread and butter. But in the context, in the more general context of non-equilibrium systems, we call it equation of state. Okay, so part one is on the birth of 2D wave turbulence. This is the idea, okay? Even if it was a 3D system, we wouldn't know how to draw better than this, but it actually is a 2D system, so this is a full representation. This is in momentum space, okay? And there's two key ideas associated with the birth of turbulence, with the emergence of turbulence starting from equilibrium. The first one is, is emergent isotropy. So here at low k, generically, energy is injected in some anisotropic way into the system. And in particular, in our case, we're injecting it with a force, and the force is a vector, so clearly, it is anisotropic. But then due to, microscopic, nonlinear interactions, beyond some wave number, the cascade actually becomes something emergently isotropic. Okay? That's the first idea. At least it's relatively common that this is the case. Maybe there's some contention, in what kind of system that actually happens or does not happen. And the second conceptual idea is the so-called dynamic or spatial-temporal scaling, which means that once you form this cascade front, this is all before a steady state has been established. Once you form this cascade front, it propagates, radially outwards, and it's supposed to propagate in algebraic way. Okay, so t is time, and beta is some negative exponent. And in its wake, it leaves this, what is going to be, steady state momentum distribution k to the minus gamma. Now, connecting this to a broader context, something that's actually very familiar in turbulence, what it means is that the full momentum distribution before the steady state is established, i.e. before the cascade front reaches the dissipation scale, and dissipation can match the injection, the full momentum distribution follows this generic, self-similar spatial-temporal scaling form. Okay? So here, alpha and beta can be anything, and this kind of, in general, and this mathematical form appears, all over the place. It is like critical behavior for, say, phase transitions in condensed matter physics, except now it's spatial self-similarity in both space and time. It is the same maths that appears in Carter-Parisi-Zhang scaling in classical physics, surface growth. It's the same maths that appears in the mathematics or dynamics of closed quantum system equilibration, which you could say that's because that is turbulence, as Natalia has done a lot of work on. So in general, alpha and beta can be various scaling exponents. In our particular case, if you have this power law distribution, then alpha is supposed to be gamma times beta. And then you can also relate the beta to gamma and the dimensionality of the system. Okay. All right, so what do we see? To the experiment, all scale pictures. What I mean by all scale, first of all, the experiment is we take this 2D box, and again, we just shake it in plane with an in-plane force, which is spatially homogeneous, but time oscillating, similar to 2D, to 3D. And what I mean by all scales picture is that we're injecting energy at a very large length scale into the lowest phonon mode, and we can picture that phonon mode directly using something called principal component analysis. And then here's the dissipation scale. So at a much larger momenta, smaller length scale, one sees this isotropic momentum distribution, and we can follow how this happens both in space and time, all the way from the individual quantum states to something that looks like a continuous momentum distribution. And to do that, I'm not going to explain much about this, but we use 3 atomic physics methods. So one is this principal component analysis, which up to a point allows you to see in situ the formal modes. And then for medium momenta, we use something called Bragg spectroscopy. And then at high momenta, we use time of flight, which is introduced now several times already. So starting with the low K anisotropy, and how we switch to high K isotropy. So first we start with with this principal component analysis, and what you can see is that you start driving this. We're directly driving only this state, okay, and then because you drive it strong and it's a nonlinear system, the spontaneous this state gets occupied, which is kind of the first step towards turbulence, and then this one, and then this one, okay. But as far as we can go, we did not recover our expected isotropy, which is expected at high K. So everything here seems completely one-dimensional. It's kind of persistent anisotropy up to a point. And so this might be actually very interesting. And then our ability to keep doing it stops for technical reasons. So everything here looks one-dimensional, and that in itself could be an interesting problem for the future because it's maybe some way, some opportunity to study one-dimensional acoustic wave cascade embedded in this two-dimensional system. Anyways, we have not seen how high K isotropy emerges, so we switched to a different system, which is this Bragg spectroscopy. I don't go into details of that, but it basically measures momentum distribution. You can do 2 separate experiments to measure the momentum distribution either parallel or perpendicular to the driving direction. Okay. And so the concept is that if you have low K anisotropy but high K isotropy, that means that along the 2 directions you have distributions which is narrower here than here, but the wings coincide. And that is indeed what you see. Okay? And you see the transition between from anisotropic behavior to isotropic behavior happens somewhere around the healing length. And there are theories that say that makes sense because of the issue is basically whether 3-wave or 4-wave mixing dominates the dynamics. Okay? And the channel for 4-wave mixing opens only at momenta above the inverse healing length, roughly, with some numerical factors. So anyways, for the future, both of these are interesting to study. How does this actually depend on the interaction strength? Can we study this more? But right now, for the kind of the overview of the birth of turbulence, we just keep going. So we had something anisotropic. Now we know it has become isotropic above some K, and then we switch back to time of flight. And so now, the here momenta are high enough to be isotropic, but they have not reached the dissipation scale yet. And what I'm showing is the compensated spectra, which means I just multiply nk to k to the gamma. So the top is flat, and you can see how the cascade front propagates from left to right. Okay, these are different times. So it propagates, and then at some point the times are different, but the cascade front looks the same because it has hit this invisible wall, which is the dissipation scale in our system. Okay, and then before it even after it hits the wall, you can plot the cascade front versus time, and what you see is initially some power law behavior until it saturates at the dissipation scale, and the line here is our prediction without any free parameters. Right? It just comes from this formula. If you have a spectrum with some gamma and you're in 2 dimensions, then beta should be something, and indeed it is. Or you could turn this around and say I measure both gamma and beta. And so I can, for the dynamics of the cascade front, I can extract the effective dimensionality of the system. In this case, it's not particularly interesting. It's just 2, because we made it 2. But for the future, it's maybe some interesting tool to look at some dimensional crossover, something that is in between 2 and 3 dimensions. Okay, and then once you've seen this, it's not hard to believe that you can collapse these curves, the pre-steady state curves, onto a single curve. Whereas once you enter the steady state, then the scaling breaks down. So to summarize this in one slide, we basically now have at least sort of the contours in both space and time, in momentum space and time, what is happening. So we started at 0, okay, and then we go to higher and higher momenta. At low K, we have some persistent anisotropy, and that actually persists even in the steady state. Okay, so in steady state, you have a coexistence of anisotropy at low K and the isotropic steady state at high K, and in between, this boundary, follows this power law dynamic scale. Okay, so I switch to the second part of the talk, which is about particle and energy fluxes, which in Richardson's poem is related to this part and so on to viscosity. Okay. So the question is, what is very generally, dissipation? And we have some intuition from classical fluids, that what it means is that hydrodynamic flow turns into heat, okay? And it's not coming back, right? But the concept is more general. It's that it's not coming back that is actually crucial. I mean, already going to liquid helium, we have learned more, because people thought like, oh, there will be like no dissipation in a classical sense. But then we realized that like, if all you're seeing is vortices, but vortices turn into sound, and they're not coming back, then for the purpose of studying turbulence in superfluid liquid helium, the transition of energy from vortices to sound, in some sense, also looks like dissipation. And so the irreversible aspect is really what defines what is dissipation in the context of turbulence. And so in our case, looking at momentum distribution of waves, we always see everything. Right? The energy flows between different modes, but you see all of them. Okay? So the only way that the energy is actually dissipated is if particles leave the system. Okay? And so the dissipation scale is just the root of the trap depth. Okay? So initially, again, we have this anisotropic forcing. Then isotropic cascade front propagates outwards in k-space. And once it reaches the dissipation scale, the particles just start seeping out. And you can count them. So it's a very simple experiment, actually, to measure the fluxes in the system. This is shaking time. This is atom loss. Initially, there is no loss. This is the pre-steady state where you see the dynamic scaling. And then beyond some time, you get this constant loss, which gives you the particle flux, from which you can trivially get the energy flux. And because this is just a trap depth, it's just the power of our laser, you can also tune this dissipation scale. And that, for example, you can use to elegantly show the zeroth law of turbulence, that if the dissipation scale goes to infinity, then you're left with the finite energy flux with zero particle flux. You cannot do the experiment there, but you can see how it extrapolates there. I'm not going to speak more about it. I just need this ability to measure flux for what I want to talk about. Okay. And so this brings me to this last few slides on the equation of state. And so this is what I mean, how we sort of placing it in a broader context of non-equilibrium physics. So, this is a pretty familiar example of an equilibrium equation of state. Okay, it's an equilibrium classical gas at pressure P and temperature T. Okay, and of course we know it's microscopic from Boltzmann. Okay, but 200 years earlier, before Boltzmann, we actually knew its equation of state from Robert Boyle. Okay, that V is inversely proportional to P at constant T. And so this succinct description holds independently of exactly how you apply the pressure. You can put an apple on top, or you can put a pear, And it also doesn't depend on the details such as what you use to provide the temperature. Right? Could be any kind of pot. Right? So all these things are sort of integrated out, and the key macroscopic properties of this many-particle system are captured elegantly by an equation of state. And so the question is, to what extent we can do an analogous thing for our turbulent Bose gas, where we're in a fortunate situation that we already know the microscopics. We actually know the momentum distribution. And this is a question which, it's interesting for turbulence. It's interesting for many other things, like active matter, glasses, and so forth. To what extent you can transpose thermodynamics-like concepts to far from equilibrium matter. Now, in turbulence, there's a long history of this, because actually the answer, though it wasn't called equation of state at the time, for hydrodynamic vortex turbulence comes just from dimensional analysis. Okay? This is the 5/3 law, but I'm not here actually interested in the 5/3. I'm interested in the fact that the amplitude of the energy spectrum is known to be flux to 2/3. That also falls out from the dimensional analysis. Now, for wave turbulence, dimensional analysis is not enough. Okay, but on the other hand, some of us, who are fans of wave turbulence, would say, okay, you cannot do dimensional analysis, but you can actually do physics. Okay. So, you can solve some models which might be approximate, but can give, more insight, assuming, that we managed to match them with experiments. So here we go. Can we match something with experiments? So this is the steady state, okay? And many of you can anticipate where I'm going. The steady state is a power distribution. If you know the exponent, then all you need to write down to define your steady state is the prefactor, the amplitude of this distribution, okay? And we also know that in order to sustain this steady state, there has to be some underlying flux. Okay? So these things in red seem to be important. Okay? But these things in red, neither of them are actually experimental knobs. That's not what you control experimentally. What you do is you do something to the system. You drive it with some force, which has some amplitude and the frequency. Okay? That's what you actually control. And so you might think like, well, maybe both of those depend on how you drive the system. Right? And they do, but in a very messy way. Okay? This is actually intimately related to the fact that dimensional analysis doesn't work for wave turbulence, okay? Because you have some, you have many special length scales, resonances in the system, and so forth. And so if you look at either the amplitude of this distribution or the flux that is supporting it, that is sustaining it, okay, they both look like a mess as a function of driving frequency and driving strength. You can anticipate some things, such as the harder you drive, the monotonically they both go up, okay, but they go up in some complicated way where these curves have different shapes and even cross. Right? However, you can again probably guess where this is going. If we integrate out all these details of how the flux is actually injected into the system and just directly relate what the amplitude of the spectrum is to what the underlying flux is, then you get the unique relations which looks like an equation of state. Okay? Now this part here, the scaling 1/3, actually at least the exponent, matches the perturbative weak wave turbulence theory, which goes back to Zakharov, 1992. Okay, but then when we go to stronger drives, then there's deviations from that. Okay, so there's some theory missing there. That's step one. But now the next question is like everything I've shown you so far is for a single gas. Right? I started with some equilibrium gas and I drove it in different ways. On resonance, off resonance, weakly, strongly, whatever. Okay. And so again, thinking in the language of thermodynamics and equilibrium and non-equilibrium equation of state, generally if you have some equilibrium system, then you can take, so the equilibrium states lie on some curve. You can take one of these points, and from one of these points, you can create countless non-equilibrium states. Okay? And then, if those happen to be stationary, they might be described by some non-equilibrium equation of state, as we have just shown. But everything I have shown so far is for a single system, single density, single interaction strength. Right? And so let's try to generalize that. Okay? And so here we vary the interaction strength by a factor of 20, density by a factor of 3, or something like that. And so these are the relations of the cascade amplitude versus the flux. And just in case it's not clear, this is not a universal curve. Okay, just so make sure we're on the same page. Okay, so what we see here, if you take a cut, for example, through this, these guys are all the same spectra. If you could not measure fluxes, you would just look at the momentum distribution. You would always see the same thing. Okay, these are compensated spectra here, but anyway, these are all the same spectra, literally within noise. Okay. But once you know how to measure the underlying flux, you see that the fluxes that are needed to support the state vary by more than an order of magnitude, depending on microscopic system parameters. However, the good news is that there is space here, on the right of this slide, okay? And so it turns out, that we can actually empirically, and it's really purely empirical construction, find a universal, completely dimensionless equation of state for wave turbulence in a quantum gas. So a couple of comments here. First of all, these things are, even if you look at the single density and single interaction strength, these things are not power laws, okay? Which means that the universal equation of state can be universal only in a completely dimensionless form. So that's the first hint. However, for wave turbulence, that's not enough of a hint to find the unique solution. So both of these axes you can scale into dimensionless form, but still you can add any arbitrary power of the gas parameter, Na cubed, which is dimensionless, okay? And so using these two as the free parameters, we find this universal equation of state. I'm done here. But this guy is not only not weak wave turbulence theory, but it cannot be reproduced by any Gross-Pitevsky-based model. Okay, it doesn't have no Gross-Pitevsky-based model can explain this in terms of the scaling with the density and the interaction strength. Anyways, and so we're sure it's right, because it works for all these parameters. It's kind of self-verifying. Actually, there's a point here which comes from Nir-Navon's old rubidium experiment. So once you have found the equation state for the potassium, you can just extract the data from experiment that was done on a different machine 6 years ago, just put in the right mass, and that falls onto this universal curve as well. And so with that, I'm done. I'm not sure how much I ran over time. So two stories. One is of seeing the birth of turbulence on all time and length scales, and the other one is about experimentally constructing a universal equation of state. And if you want to discuss during the break, I mean, people might be losing patience. But in the spirit of this workshop, there's a bunch of ideas where we want to go into the future by looking at both waves and vortices, both direct and inverse cascades or bidirectional cascades, intermittency, quenches between stationary non-thermal states, connections to thermal relaxation, thermalization. Some of these we already have preliminary data for. Some of it is just, what do you call a spark in our eye or something. Yeah. All right, but this is what's done for now. Thank you very much.
Thank you very much. Okay, we have one or two quick questions, and then we continue.
about this.
Actually,
graph on the
I
right.
think we're less late now than we were at the end of Natalia's talk. So we can't have done so badly. We're now 8 minutes late, and we used to be 10 minutes late. So it's not my fault. Okay.
Okay. Shall I start?
Yes, please.
Okay, about this graph on the right and your statement, basically, Gross-Pitayevsky, what cannot explain.
Yes.
Can you specify in wine? Okay, so you did this fit on this gas parameter, right, on both vertical and horizontal axis, so empirically you collapse on a single curve. But how from this it follows that Gross-Pitayevsky is not working? I
Yes.
kind of not immediately see.
Yeah, no, you cannot. I mean, I had to ask Georg several times. Georg's in the audience. Right, so as I was saying, the first point is like you want to make everything dimensionless, okay? And so you can count the seconds and the kilograms easily, but you can't count the meters easily, okay? Because there's various ways to put the meters into the problem. That's why this gas parameter NA cubed can appear with any power, okay? And so then you get what the result is empirically, right? Actually, I think I screwed up something here. Okay, this one you should look at. Anyways, and then once you get it, then you look at the structure of the Gross-Pitayevsky equation. How would you make it dimensionless? Okay, and basically the Gross-Pitayevsky equation, however you're going to approximate it afterwards, okay, it doesn't allow the nonlinearity to enter in any other form except the product of density and scattering length. Okay, and from that it follows in this language that n naught, which is the amplitude of the cascade, divided by the total density, can be an arbitrary function of epsilon divided by n and any power of na, okay? But even with all that freedom, you cannot reproduce anything that has this non-zero alpha and non-zero beta.
So it can enter in any power, you just cannot explain power. Is that, I understand you correctly?
No. So Gross-Pitayevsky will allow you that the solution depends on na to any power, okay? Yeah. But still the number, the power for n and the power of a has to be the same. Right. And here it's not. In that sense, it violates it. Okay, I mean, violates it experimentally. So I can tell you how much. It's not like particle physics, but like, so the chi-squared, if you try to say how good the collapse is 10 times larger for something that would be consistent with Gross-Pitayevsky than for the optimal collapse.
But I mean, your spectrum is still consistent with Kolmogorov-Zakharov spectrum, right?
No.
Based on the linear shading,
This thing, you mean? Huh? This 1/3, you mean?
No, I mean the initial spectrum which you showed, power law spectrum.
Ah, yes, right, yes.
So it's not like it's completely irrelevant.
Oh no, not at all. So many things. I can show you actually how well it does. Maybe I can put this up. Okay. So yes, the Kolmogorov-Zakharov. This is offset for clarity. Okay. Kolmogorov-Zakharov has this logarithmic correction right here, and over our experimental range that actually looks very good. So this is our simple power law, modified power. I mean, power law with the modified exponent is a solid line, and the Kolmogorov-Zakharov is the dashed line. So that's great. Okay. And then there's this weak. Now this is already an approximation. Okay. So this is not any Gross-Pitayevsky, but specific weak vector Bose approximation. So this is no free parameters. Comparison of all our data to a single curve. That comes from, the prefactor comes from these recent papers from Sergei Nazarenko and colleagues, okay? And so, if this was all you knew, you would be like, well, it's not so bad. It kind of follows and just within a factor of 3, okay? However, this still, has 10 times larger chi-squared than the actual, collapsed universal curve. Right? So it's a mix. The spectrum matches, right? And for single interaction strength, the kind of equation of state that at low drive with the power law 1/3 matches, okay? But once you try to explain all densities along interaction strength, then not only does it deviate from 1/3, but even the scaling with N and A cannot be explained by GP. So there's something going beyond.
Okay, next question, 20 seconds, okay?
Okay, so you mentioned that the condensate fraction will change when you force the system because you're injecting energy. So is it possible that you should interpret this as N naught A rather than NA? So it's the condensate fraction, which then will allow you to play with the ratio of the powers of the two.
Yes, yes.
Yeah,
it's possible, and I think I will have to refer to students maybe during the break, okay? Yeah. So basically, like, what we do is try to be maximally agnostic, and I think people can correct me, because we discussed this many times, is that you can say like, yo, how about if you say, yo, let's normalize with just the condensate density and not the total density, okay? And then you say, if now I give all the freedom I can while respecting dimensionlessness, okay, what's the best you can do? And I think what's the best you can do is not as good as this, I think. Okay, work? Yes, okay.
Thank you very much. Let's thank the speaker again. And we continue the discussion over coffee during the break, okay? We'll be back now in 20 minutes, actually. So.